term. The first thing is that the talk is going to be recorded, so if we're going to have a question during the question and answer session, and you don't want to be recorded, please tell us afterwards, and we'll just cut you out. So tonight we're hosting Professor Jonge. He's currently studying Professor of Natural Philosophy at the Mathematical Institute, University of Oxford. And he's also Director of Oxford Centre for Nonlinear Partial Differential Equations. Between 2003 and 2006, he was President of International Mathematical Union. For his work, he was awarded many prizes, including Whittaker Prize and David Crighton Medal. And tonight he will be talking about what can mathematics say about liquid crystals. So please join me in welcoming Professor Jonge.
Well, thank you very much for the invitation to speak. So I'm a mathematician, right? So I spend half my time working on solid crystals, actually, and half the time on liquid crystals. So liquid crystals is a sort of newer interest for me. Now liquid crystals are a very sort of interdisciplinary subject, sort of involving chemistry and physics and engineering and mathematics, even the biosciences. And so I certainly don't pretend at all to be an expert on everything about liquid crystals. Very far from it. But I think I understand a little kind of niche concerning the mathematical description of liquid crystals, or at least I understand a little about that little niche. So I'll try and tell you something about this. So now, there will be some equations at certain points, but if you don't like, too many complicated equations, there's also lots of pictures and stuff which I think are kind of interesting. So now on the right there, so you might wonder why the king was there, ancient king. So that's a bistable liquid crystal display. So that's interesting that. I mean, most liquid crystal displays, like you find on your watches, if you turn off the current, they disappear. But newer kinds of bistable displays they retain the image when you turn off the current. So that's a sort of stable, some kind of stable configuration of the pixels. So that's one of the newer sort of technological aims that people have. So they have visions of sort of electric paper, which you can, I don't know, you go on your commuter train or something and you carry your electric paper as you pass something, you just plug it in and there's the Daily Telegraph or something, or Guardian, whatever. And it stays there and just doesn't disappear. So whether this can happen or not, I don't know. Anyway, so liquid crystals are an absolutely huge industry. Many of you will have them on your wrists or laptops or something like this. And the working substance, liquid crystals themselves, are a kind of intermediate state of matter, somewhere between liquids and solids. So liquid crystals flow like liquids, but at the same time they retain some order of their constituent molecules. So I'll try and show some things. So they can be classified in lots of different ways, but the three main classifications are nematics, cholesterics, and smectics. So I've worked mostly on the easiest, which are nematics. I've graduated a little onto cholesterics and hardly done anything on smectics, which are more complicated. So nematics consist of rod-like molecules. So maybe length 2 to 3 nanometers, for example. So there's two different kinds of liquid crystal molecules. One's called MBBA, and the one below is 5CB. These are two different kinds. And there, on the top right-hand corner, you see a sort of a space-filling model of one of these molecules. So we think of them as being rod-like, but you can see actually that they're not exactly rod-like. They have a quite complicated shape. And I was hoping to have an internet connection to be able to turn one of those pictures round so you could see it three-dimensionally, but unfortunately there's no internet connection, so I can't. So depending on the nature of the molecules, and the interactions between them and the temperature and so on, they can arrange themselves into different phases. And so typically at a high temperature, liquid crystals will have no orientational or positional order, and so they will behave like an isotropic fluid. So it just flows like water or something. Now, here are three possible liquid crystalline phases that you might get when you reduce the temperature through some critical temperature. So on the left is the nematic phase. So there you see that the molecules are sort of rod-like. They're represented here schematically by ellipsoids. They're more or less pointing in the direction of that arrow, vertically upwards. They're not perfectly ordered, but more or less their average order is vertically upwards. They're like sort of matches in a matchbox. They're not perfectly lined up, but a few of them may be not in exactly the right direction. But anyway, that's what they look like. Now, so that's orientational but no positional order. Now the smectics, so that there are schematic pictures of two smectic phases. And the first one is called smectic A. And you see that, again, they're essentially pointing, say, vertically in the direction of the arrow, but they also arrange themselves in layers. So there's some, as well as orientational order, that they're pointing, say, vertically upwards, there's positional order in that they're sort of end to end. They're forming these layers. And then in the smectic C, there's some kind of inclination in the layers. This is a more complicated kind of phase. So these have sort of orientational and some positional order. Now, of course, they're moving around due to thermal motion, so it's a little bit misleading to think of everything as being a kind of static-looking picture like that. So they're wiggling around due to thermal motion, both as a whole. So you take this whole molecule, it'll be wiggling around due to thermal motion, and of course, inside the molecule, the atoms are vibrating due to thermal motion as well. So that's, of course, so you immediately start realizing this is an incredibly complicated problem, and so you have to make some sort of simplifying assumptions to try and analyze it somehow. So it's very difficult to actually see this nematic order because it's unlike, say, solid crystals where you can use transmission electron microscopy. The atoms sort of line up nicely in columns. You send the electron beam that way. And so there's nothing like that in liquid crystals. So to image them, to image the molecules themselves is pretty difficult. This is one of the rare kinds of pictures that in fact, the only picture really that I've seen. I think this is in tobacco mosaic virus, which forms a sort of liquid crystal. So probably a sort of much larger scale than typical nematics anyway. Okay, now cholesterics, they're also rod-like molecules, but they have an inherent chiral nature to them. So you can add a sort of chiral dopant to a nematic. And so, for example, they would like to line up with a twist that changes in the vertical direction. So if you look at, say, at the bottom there, they're sort of pointing in the direction sort of left to right, and then the next layer up, they've turned a bit, and the next layer up, and after you've gotten to, so at the bottom it says AB, and then it says BA. So then they've twisted through 180 degrees, and you go right up to the top, they've gone through 360 degrees, and so they're back where they are. So that's the typical picture of a cholesteric. It forms these kind of helical patterns. Now, so as I said, these liquid crystalline phases appear when you reduce the temperature through some sort of critical temperature. So, so let's suppose that critical temperature is theta critical. So above theta critical, for temperatures theta above theta critical, it's an isotropic fluid. Between theta critical and some lower temperature, it might be a nematic liquid crystal, and below that, below theta m, something else has happened. It's either solidified into a solid crystal, or it's maybe changed into a different liquid crystalline phase. So there's all manner of complicated things that can happen. But the simplest, I'm just going to be interested in what's happening to the right, above and below theta critical there. And so those are the temperatures for MBBA. So that's a relatively small range of temperatures in which MBBA is a nematic. So here's a picture. So this is taken from a very good website in Cambridge where you can get all sorts of freely usable pictures on videos and things on material science. And this shows the isotropic to nematic transition. So I'll see, I'm going to run it if I can find the place. There we go. So now you're just reducing the temperature, and this is the liquid crystalline phase condensing out of the black nematic phase. And one thing you see here is lots of defects forming. So these kind of patterns are kind of defects, and I'm going to talk a bit about what defects are and how we sort of model them. I mean, you don't want general defects like this in your watch. So how can we try and describe this? So the simplest kind of description is a so-called director description. So we try to represent the mean orientation of the molecules, if you like, the direction of the arrow that I showed, by a unit vector which depends on position x in the fluid and time t. So we call that director n of x and t. So that's what n would be near some point, maybe. But immediately we see that there's a kind of sort of mathematical difficulty here, which is that these molecules typically are viewed as being more or less equivalent if you turn them over. At least in the bulk, they're equivalent. Maybe each one might be slightly different, but on the whole, it's viewed that they should have the same behavior if you turn them over. And so, so there's no real physical meaning to the arrowhead on that n. Okay, it points upwards, but it might as well have pointed downwards. From a physical point of view, that's the same thing. So really, a better description is not to think of a vector field, which is a vector that, that points in a certain direction at each point x and t, but rather as a line field, so there's a line at each point, so that the orientation of the molecules is parallel to some line, so a line through the origin or something. Okay. Now, I'll come back to that a bit in a second. Now. So how do these liquid crystal displays work? So the usual method is the so-called twisted nematic display. So you have to think of this as being corresponding to a single pixel. So if it's going to be black and white, this pixel is either going to be black or it's going to be white. Now the pixel is contained between two plates, and the plates are treated so that on say, the bottom plate, there's the liquid crystal molecules have some preferred orientation. You can do this, for example, by rubbing the plate in some way. You get, so the liquid crystal molecules say want to point in, say, the direction of my fingers like this. But on the top plate, it's treated so that they want to be in a perpendicular direction. Okay. Now, also, there are polarizers on the top and bottom plate. So the polarization of the light that is let through the bottom plate is again perpendicular to the polarization of the light that's let through the top plate. Now, if you look at the sort of the red liquid crystal molecules, they've got to match the boundary condition on the bottom plate and the boundary condition on the top plate. So what they naturally do is to form a sort of helical structure. They gradually turn. So by the time they've got from the bottom to the top, they've turned through 90 degrees. And due to the interaction of light with the liquid crystal molecules, the polarization turns as well. So that in this situation, with the plates treated and the polarizers, as I've said, the light passes through, and so the pixel is white. Okay. Now, if you turn on the field, so then say a vertical field, then the molecules want to align parallel to the field. Of course, they can't do that just close to the bottom plate or just close to the top plate, but most of the place they're going to point vertically upwards, and so the liquid crystal molecules don't change the polarization. And so if the light's coming down from the top, for example, it goes through the top polarizer, but when it comes down to the bottom, the polarization is wrong, and so the light's not transmitted, and so therefore the pixel is black. Okay. So that's the sort of idea. It's quite complicated, of course, right? But that's the idea. Now, how are we going to model? How are we going to model this? So a very natural idea is to model it, is to try and model the motion of each molecule. Okay, so that we do this via molecular dynamics. I don't do it by molecular dynamics because it's a very difficult thing to do, but I know people who do it by molecular dynamics. So that means that you take two molecules and you somehow represent interactions between them and so on, and then you run the simulation. So now, and I'm going to show you a Monte Carlo simulation done by the group of Claudio Zanoni in Bologna, who is probably the best in the world for doing this. And it's done, but he does many different kinds of simulations, but this one is done by using what's called the Gay-Byrne potential, which models the interaction between different molecules. So the different molecules here are represented by ellipsoids, and this interaction potential, which is a complicated kind of formula, it's some kind of anisotropic version of the Leonard-Jones potential between point pairs of atoms or molecules. Okay, in any case, apart from that, it's just Newton's laws. This gives you the interactions between the molecules, and then you run the simulation using Newton's laws. And it is a simulation of the twisted nematic display. And so before I show it to you, I just want to explain the kind of color code, right? So so on the left, you see that there are different colors that represent the orientations of the molecules. So blue is vertically upwards, red is in this direction, and green is in the perpendicular direction. So you see that okay, so we want to model the twisted nematic display. So that means we want to impose a boundary condition that the molecules are pointing in one direction on the bottom plate and in the perpendicular direction on the top plate. And the way that's done in this simulation is by fixing, say, 9 layers on the bottom and the top, fixing the orientation of 9 layers of molecules on the bottom and on the top. Okay? And then everything else interacts both with those molecules whose positions are fixed and with all the other molecules. Okay? So the initial condition is taken to be that it's vertically upwards in between the two plates, and then you just run it and you see what happens. And this is actually a still from it. And of course it's quite difficult to interpret what's going on, but it turns out that you can take sort of statistics of these molecules, and you find that indeed the mean orientation gives this helical form. Okay, so now I'll try and run this if I can find the. Where's it gone? Here we go. And what's going to happen is we're going to do the simulation. Or he's going to do the simulation twice. Once without the voltage, and you're going to see the view from on top as if you're looking at the light being transmitted through it, and you'll see that it's dark without the voltage. Okay, as the helical pattern gets formed, and then when you put on the field vertically, you'll see eventually it becomes white in the simulation. So here we go. Okay. On the right is looking down from the top, and on the left is looking from the side. So you should now it's going gradually from green to blue to red, and that's this helical form being set up. And on the right, you see it's become white. The light is being transmitted through. And now he's going to turn on the field, and you see it become, well, it's mostly applied in the middle, so it's becoming blue in the middle. The field is making the the molecules go vertically upwards, and in that region, looking down from the top, you see that the pixel has gone black. Okay, so that's so this is one way of, okay, so how many, there was about 1 million molecules in that simulation. So that's a pretty high, it's a pretty intense, computational intensive calculation, and you can see anyway that we didn't actually see a helix there, right? I mean, that's not, it's not so obvious how you get a helix from this picture. You have to do some processing of the data to see that. So it's not, in some sense, it's too complicated a way of trying to model this situation. So most people use continuum models. But of course, it's very important to do these simulations because they inform, you know, the kind of hypotheses you make. So now, so here's a continuum model. So we take some container, some region of omega of three-dimensional space, which is filled with this liquid crystal. And we're gonna keep things simple. I'm just going to consider static configuration, so the fluid velocity is going to be 0. Now, I mean, the problem of the flow of a liquid crystal is incredibly complicated. It's, I mean, we don't even understand, from a mathematical point of view, the flow of water, let alone the flow of a liquid crystal. So you can get $1 million, actually, by proving that the Navier-Stokes equations have smooth solutions. They're the ones that govern the flow of water, and these are much more complicated. So now, so there's omega, and somewhere in that picture there should be a tiny little black dot, which is the point X. So I'm looking at the point X, and I'm going to blow this up. I'm going to sort of magnify what's going on near this point X. So so on the left here we see just a magnified version of the ball center X radius delta, which I write as bx delta. So that's the just so that we can see what's going on. This particular ball is very, very small, right? Very small so that it's almost a point, but large enough to contain a decent number of molecules so that we can represent some kind of average orientation there. So it's filled up with all these molecules, right? Enough of them to get an average. And so now we pick one of these molecules at random from that little ball there. And so it will have an orientation that is given by some line through the origin that's parallel to the long axis of the molecule, right? So you can represent that in different ways. You can represent it as a line through the origin parallel to P. So mathematicians have a trendy way of describing that. They call it RP2, the real projective plane. But it's just lines through the origin. Or you can represent it, as is done in this picture, by a pair of antipodal unit vectors. So points on the opposite points on the sphere, and the line is represented by the line joining these opposite points on the sphere. Or a very smart way to do it, it looks very complicated, but a very useful way to do it, is to represent it by a matrix. A 3x3 matrix, P tensor P, whose ijth component is Pi Pj. Now, why is that an interesting thing to do? Well, I mean, there are sort of some deep mathematical reasons for it, but the point is that from the matrix P tensor P, you can recover the line, but of course, if you change P to minus P, P tensor P remains the same. Okay, so it's a way of representing mathematically lines through the origin. Okay, and it turns out that this is central to one of the most important models of liquid crystals. Now, I've said that we're trying to average over space somehow. We're going to see what the typical orientation of a molecule taken from this little ball is, but also things, of course, varying with time. So probably we should really average over some little time interval as well, but I'm not going to do that because I'm not considering time. Okay. All right, so let's imagine then taking, to go back to where we are, let's imagine taking molecules at random from this ball and seeing what the orientation is. So I take one molecule, I get one line through the origin. I take another molecule, I get another line. I take 1,000 molecules from that little ball, I get 1,000 different lines, right? And I want to represent this by the probability, a probability distribution for lines, for particles, for molecules taken at random from this ball, right? So we represent it by a probability density function on the sphere. So the sphere is called S2. And so that means I have, if I want to know the probability of finding a molecule in some set on some symmetric set on the sphere, I just integrate this function rho of p over the sphere, over that pair of opposite sets, E and minus E. So it's a probability distribution on the sphere, and it satisfies that rho of p is rho of minus p. That's to get this head-to-tail symmetry. Okay, it doesn't really matter what the details are here, you'll see. But anyway, this is an unknown. And so now, to have a probability, to have a model which has as its basic variable a probability distribution at each point, that's very complicated. I mean, that's an infinite number of variables at each point. That's far too complicated to be practical. So what Dejenne, who got a Nobel Prize for it, decided to do was to represent it instead by moments of the probability distribution, which is a very classical idea in physics and so on. So, but the first moment is you integrate the vector p over the sphere times this probability. And because rho of p is rho of minus p, that turns out to be 0. So the first moment gives you no information about the probability distribution at all. So you go for the second moment. The second moment is defined to be, you integrate this matrix against rho over the sphere. Oh, okay. So you get some matrix M. And it turns out that this is a non-negative matrix whose trace is 1. Okay, so the details are not terribly important, but what is important is that the variable is a matrix. It's a 3×3 matrix. And this matrix is some kind of, well, it is the second moment of the probability distribution of orientations at a particular point. Now, Dejenne, and he got a Nobel Prize, so we shouldn't attack him, didn't like matrices whose trace was 1. He liked matrices that were whose trace was 0. So he subtracted from M the value that M has for an isotropic fluid. That means the probability distribution is just 1 over 4 pi. It's uniformly distributed over the sphere. You've got an equal chance of getting any orientation for a molecule. That's the isotropic fluid. So then it turns out that M is a third the identity matrix. So he subtracted that away from M, and he called the matrix that was left Q. So Q is M minus M0. And then Q is a symmetric matrix. Its trace now is 0, and it inherits some very interesting eigenvalue constraints, which I'm not going to talk about. However, so this is a 3×3 matrix. If you know any algebra, then you know that it's a symmetric 3×3 matrix. So symmetric 3×3 matrices have 3 real eigenvalues. Now, if 2 of them are the same, you can represent Q in this form: a number S, which is called the scalar order parameter, which is some kind of scalar that represents the degree of ordering of the liquid crystal molecules, times n tensor n. Remember, that was this matrix whose components were Ni, Nj, minus a third the identity matrix. So if 2 of the eigenvalues are equal, then Q has this form. And it turns out that it's practically impossible to measure any configuration of a nematic liquid crystal which is not of this type. Okay, so, and that's we'll try and see why that is in a moment. Okay? So typically, you'd measure Q. That's not a trivial thing to do, of course, but you measure Q, and you find that it has this uniaxial form. 2 eigenvalues happen to be equal. S is typically between 0.6 and 0.7. It can be different. So S equals 1 means that all the molecules are perfectly ordered. S equals 0 means that there's no ordering at all. The typical value that you get between 0.6 and 0.7 says that they're pretty well ordered, the molecules. They're pretty well ordered. They more or less point in the same direction. Okay? Now we'll see why this is to be expected later. Now, what did Dejenne suggest? So he suggested that, well, at each point x, we have this tensor, which he defined. He called it his Q tensor. So it depends on x, right? So it's a symmetric matrix describing the ordering of the molecules. And then he says, okay, let's calculate the total energy of the molecules over the whole container. And let's suppose that that energy is got by integrating some energy density, which is of C, that depends on this matrix and its spatial gradient. And of course the temperature, okay, the temperature state. So, but the important thing is that the energy density is supposed to depend on this ordering matrix Q and its spatial gradient. And then you're supposed to find the Q, in a particular problem, you'd have some boundary conditions for Q, and you'd like to find the Q as a function of x that minimize this energy subject to the boundary conditions that you have. That would be the kind of problem that you try to solve, e.g. for a twisted nematic cell. And, well, Dejenne proposed a kind of explicit form for this energy density. So I've taken a simplified form of it. Doesn't look very simple maybe, but okay, so it consists of two pieces. So the first piece depends only on the matrix Q and not on its gradient. Okay? And it is, well, it's not important what the actual sort of, for our purposes, what the actual formula is, but you see it's a quartic function of Q. So it's a polynomial, it's a quartic in the matrix Q. And it depends on theta through this coefficient of the first term, which is proportional to the temperature theta, and there's some critical temperature theta star. And then the dependence on the gradient of Q is just epsilon times the gradient of Q squared. And the gradient of Q squared is just the sum of the squares of all the partial derivatives of the elements of Q with respect to all the coordinates x, k. And so therefore you've got to, and so they're called the bulk energy of CB and the elastic energy of CE, and so you've got to find a Q that minimizes the sum of these things. Right, so now, so here you can do something that's interesting. So you can say, right, well, let's suppose that we ignore this second term for a moment and see what the Q is that minimizes the first term. So that's just a quartic function of Q. So you do the calculation, and you find the matrices Q, which they've got to be, remember, symmetric, trace-free matrices that minimize that quartic function. And what you find is that there's a critical temperature, theta Ni. Ni stands for nematic initiation, which is given by some formula in terms of the parameters, is not important. And the unique minimizer of that function, if you've got a temperature that's bigger than that critical temperature, is Q equals 0. Now, Q equals 0 means no order. So that means that above this theta Ni, it's an isotropic fluid, according to this model. Whereas if your temperature is less than this critical number, theta Ni, then Q is uniaxial. It has this form S min, some number, times n tensor n minus a third the identity. N is a unit vector. S min is given in terms of the various parameters. So somehow that's, in this model, supposed to be the reason why we only see these Qs which have two eigenvalues the same, that they are the Qs that minimize the bulk energy. And then the elastic energy is supposed to be something very small that doesn't change that very much. You've added on some very small term, but still, effectively, you get things that are very close to minimizing the bulk energy. And so this S min is a specific number which you would, for reasonable numbers, would come out, say, between 0.6 and 0.7. Okay? Right, so this model, therefore, predicts that there's a phase transformation from an isotropic fluid to a uniaxial nematic phase at that critical temperature. But that's pretty complicated. It's still pretty complicated because you've got now a matrix at each point that you've got to evaluate. That's not such an easy thing to do, and you know, there's actually, I've given you a very simplified version of the energy functional. There are actually many more constants in the elastic terms that are typically used. Okay, so, but on the other hand, I said that, well, you only see things in general which are uniaxial. So that suggests that we simplify the model by assuming that everything is uniaxial. Okay, so instead of trying to minimize bulk energy plus elastic energy, I suppose that I've already minimized the bulk energy, and that gives me this constraint that Q has this form. And among those things, I minimize the elastic energy. Okay? And if you do that, so you can take this Q, now S is a constant, N depends on X, so I can calculate formally its gradient. I just do it, you know, I've got to calculate sort of d by dx k of Ni Nj, so I just work it out. I get sort of terms with in N and the gradient of N. I shove that back into this Landau-Dejenne form. Okay, so in this theory, you're going to minimize you're going to try and minimize this. And so what does this turn out to be? Well, it turns out to be just a constant times the gradient of n squared. And that's what's called the Ozone, or this is a simplified case of the Ozone-Frank theory, which is the oldest theory of liquid crystals. And so then in Ozone-Frank theory, n is a unit vector, and you just have to minimize, well, in this particular case, just the integral of the gradient of n squared. But you have to do it subject to the constraint that n is a unit vector. So although it looks like a linear problem, it's got this unit vector constraint to it, which makes it a highly nonlinear problem, actually. So this may look simple, but it's not as simple as you would think. So that's the Ozone-Frank theory, and so that's used. I mean, that's the typical theory that's used for the liquid crystal displays, for example. However, there is an interesting thing which I alluded to at the beginning, which is that in this Ozone-Frank theory, n is supposed to be a unit vector, but I said that that's not a physical thing to do. It's not. This arrow is just not physical. I mean, it should be a line. It shouldn't be actually a unit vector pointing in a particular direction, because up is the same as down physically. So the question is, if you had this Q which had this form, could you find an n whose orientation sort of changes nicely? So so this may or may not happen. So it's better to see this in a picture than rather with mathematics. So here we go. So here's an interesting situation where the dotted lines, the line field has to be parallel to the dotted lines. Okay, so this is the region outside a cylinder, say, in black, and so the line has to be, first of all, in the plane of the picture, so it has no component in the perpendicular to the screen, and it's got to be parallel to the dotted lines. Okay, so can you orient this? In other words, can you assign an arrow to this line field in a consistent way? And we'll see that you can't, actually. So let's try to do it. So on the left, we've got two choices, really. We can either have all the arrows pointing to the right or all the arrows pointing to the left. So let's suppose we take them all pointing to the right. Then, well, if everything's going to vary smoothly, they're going to have to, when we go over the top there, they're going to have to continue pointing in the same direction. But then when we come down to this sort of blue region, we see that there's a conflict, that the arrows are pointing both to the right and to the left. So that sort of shows you that, in fact, this issue about giving a direction to the arrow is a serious one if you're in a region which is not sort of simply connected, has holes and stuff. And actually, then the Ozone-Frank theory has to be sort of modified somehow. Okay. So I'd like to finish by talking about defects. So we saw defects appearing in the movie I showed you of the isotropic nematic transition. So now in this theory I described, or the Ozone-Frank theory, these defects are described by actual singularities in the vector field n of x, or the line field, or the corresponding line field. So here's a picture from the lab of Oleg Lavrentovich at Kent State University, which is one of the best liquid crystal groups in the world. These are what's called boudrums. They're, the defects here are the points at the centers of these kind of interesting patterns. So there's one here, for example. That's about the only one I can, or that one I can reach. There's one here. So the black and white is just an indication. It's a picture taken in polarized light, so that so the black and white is telling you something about the orientation of the molecules. But these are point defects. So they're sitting on the surface, actually. So I mean, this is a picture of something between plates, and these point defects are actually on the surface. Okay, so, but they're singularities in the director field. And so you can say, well, let's see what kind of singularities we can make mathematically, if you like. So that's what it is in the Q tensor theory, and it's n of x in the Ozone-Frank theory. So the simplest kind of point defect, remember n of x has got to be a unit vector. Okay, so the simplest kind of defect you could think of is the Hedgehog defect. So that means that the n of x points radially outwards from a point. So let's try to describe it on the top right-hand picture. So each n of x is a unit vector. It points radially outwards from the point from 0, and so the form of it is n of x is x divided by the length of x. Okay. Okay. So now, well, we can calculate what the gradient of n of x is, and it turns out to be 1 over the length of x, the vector x, times the identity minus n tensor n. Of course, n is a unit vector. It's x over norm x. And the gradient of nx squared, therefore, is of order 1 over the length of x squared. Okay. So now, let's see whether this defect has finite energy or not. So the energy is the integral of the gradient of n squared. So if I use r to denote the radius, so if you remember how you change variables and integrals, so the radius is going from 0 to 1, you have this squared is 1 over r squared, that's r to the minus 2, and the change, for the change of variables, you have an r squared. That's because you're in 3 dimensions. You get r squared dr, d theta, whatever. And so you see that the energy of this is proportional to the integral of r to the 0, okay, which is finite. Okay, excellent. So there's a possible singularity, which actually is an equilibrium solution for these theories. Sometimes it's a minimizer of the energy subject to its own boundary conditions. And the point is it has finite energy. Okay, so that's good, because you see it sometimes, these point defects. In fact, the ones we saw in the picture before were sort of like half of these defects, because the center is actually sitting on one of these surfaces. Okay, so finite energy, excellent. Now here's something else that you see, which is the 2-dimensional version of this. So now you take a cylinder, and the vector points radially outwards from the generating line of the cylinder. Okay. So now n of x has this form. It's a vector, of course, 3-vector. So it has components x1 over the radius, x2 over the radius, 0. And the radius now is the 2-dimensional radius. So it's the root of x1 squared plus x2 squared. And now you calculate the gradient of n squared, and it's 1 over r squared. But the r is now the 2-dimensional radius. Okay. And now when you calculate the energy of that, because it's two-dimensional, you have r to the 1 instead of r squared. So it's the integral from 0 to 1 of r to the 1 minus 2 dr, and that's infinite. Okay, so that's one of the big, for a long time it was a big sort of, well, it still is a big sort of issue somehow in this theory, because there's a singularity that you see in some sense. In some situations you see this singularity, but according to this theory, that singularity has infinite energy. Okay. So obviously something's gone wrong in the model, right? So I mean, that can't be right somehow. My first reaction when I saw this was that, well, you see that it's coming from the fact that it's the gradient of n squared. If it had been the gradient of n to the 1.999, you wouldn't have had this problem. This energy would then have been finite. Okay. So I mean and that's actually quite an interesting thought. But I don't have time to go down that sort of route. Now there are some other kinds of singularities which are even more disturbing. You see them, and they're called index 1/2 singularities. So here's a sort of schematic on the left. So again, these lines are in the plane of the screen, and so the director field is supposed to be parallel to these lines. Okay, and on the right you see one of these index 1/2 defects in a material that's formed from lots of carbon nanotubes. And when you take a mixture of lots of carbon nanotubes, they form liquid crystals. I mean, they behave like liquid crystals. And you see you get exactly this kind of singularity. And you get these singularities in liquid crystals often. And there's another index 1/2 singularity, which is like the one I showed before, but when the radius of the cylinder is 0. Okay, so it's exactly the same picture. And these have infinite energy as well, and yet according to these models, but still according to these constrained model, and also it's I should go back. They're not orientable either. You cannot orient these. So and here you've got a simply connected region. So if you try to assign, there's no consistent way of assigning arrows to this picture. Okay, so you see here that in liquid crystals, issues of topology arise really naturally, and so these are essentially topological questions here. Okay, now one of the great advantages of the Landau-Dejenne theory, well, there are two things that it in principle does at the same time. One is that it removes this problem about the sign of n, whether it's pointing one way or the other way, because it's expressed in terms of n tensor n, and so you don't have, it's naturally invariant to that reversal of molecules. And the other thing it's said to do, it's supposed to make these defects have finite energy. Okay, but how does it actually do that? Well, here's the energy functional again. So remember, now the unknown is a matrix Q that depends on X. And so we want to find a Q of X that minimizes this integral. Okay, now, if you know something about getting what's called the Euler-Lagrange equations for integrals like this, so in other words, the partial differential equation that's satisfied by, say, any kind of local minimizer Q of such an energy function, then there it is. There's the Euler-Lagrange equation. Well, it's actually a family. It's a system of partial differential equations for the components Qij of the Q tensor. So, okay, so that's what they are. So on the right-hand side, you've got derivatives of the bulk energy with respect to Qij, so the bulk energy was quartic in Q, so what's on the right-hand side is some kind of cubic in Q. And on the left-hand side, we've got a multiple of the Laplacian of Qij. So if the right-hand side was 0, this would just be Laplace's equation for Qij. But they're all coupled, of course, so there's a system here. Now, partial differential equation, I direct this center for partial differential equations. Okay, so now partial differential equations come in lots of different types, and the nicest possible kind of partial differential equation you can have is something like Laplace's equation. You know, Laplacian u equals 0, or Poisson's equation, Laplacian u is equal to f. And these are what are called elliptic equations. And the great thing about elliptic equations, at least the great thing about this elliptic equation, is that every solution of this equation is smooth in x. Okay. So that's great. Every solution of that equation is smooth in x. So any minimizer q of this integral is a smooth function of x. Well, on the other hand, that's a problem, because you see in the previous theory, defects were given by singularities of the n. But now I'm saying that q has no singularities, all right? So that means that in the Q tensor theory, the defects have to be interpreted differently. So the defects are regions where somehow Q is changing extremely rapidly. Okay? But on the other hand, their location is not very precisely defined, and somehow the prevailing way of thinking about this is that somehow you should think of the defects as being places where the eigenvectors of this matrix have discontinuities, which can happen even when the matrix depends smoothly on x. Anyway, this is not the details of this are not important, but I think there is an interesting sort of general point here, which I'm going to try to explain. So anyway, just a little bit more detail. So, for example, the hedgehog, x over norm x, that's a description of a point defect in the Ozone-Frank theory. In the Q tensor theory, of course, you want something that looks more or less like x over norm x, and it will look very close to that, except when the radius norm x is extremely small. Okay. And then when you work out the solution of these equations numerically, you find that there's something called a biaxial torus very close to the origin. So the function's a smooth function of x. It no longer has a singularity. But of course, when you're outside a tiny little region around the origin, it looks like it looks uniaxial with n of x equals x over norm x. Okay. However, as I said, it's very difficult experimentally to know whether this is truly correct or not, because you just cannot get close enough to the core of the defect to see what Q of x is doing. Okay, so there's a big article of faith here. I mean, most physicists believe in the Dejenne theory, but it differs from other theories only in regions where you cannot experimentally observe things. So that's a little bit awkward. Okay, so but I think I wanted to make end with a kind of general sort of thing about defects, not just related to liquid crystals. So here we have an example in this theory of in these theories of liquid crystals. We have a very typical situation which arises in theories of physics. So we have a defect. Okay, so now there are lots of different materials have lots of different kinds of defects. So imagine, for example, we have a fluid. So fluids, one kind of defect that a fluid can have is a shock wave. Okay, so here are pictures of shock waves. Okay, so shock waves, loosely speaking, are surfaces where the fluid velocity jumps. Okay, responsible to sonic bangs and so on. These are pictures of such things. Or we might have a vortex. This is another kind of defect that a material may have, a fluid may have. Here's a wonderful picture of a vortex generated by the wings of an airplane. And it was done by flying the airplane through a cloud of red gas. So that you got this wonderful picture there of the vortex. So here's another kind of vortex that you get, a tornado. So that's, in some sense, a vortex filament. Okay. So those are two kinds of singularities. Or you might, in solids, you may have cracks. So there's sort of cracking in a glaze. So that you can think of as a discontinuity in the deformation of a material. So a place where the displacement of the material jumps. So I mean, if I take a piece of chalk, you know, I can break it, and that's a kind of singularity in the material. So somehow the deformation has jumped, right? And actually, an interesting question about liquid crystals is why don't we allow the director to jump? Okay, so why can't we get, you know, a surface in which the director goes like this? So this is an interesting question. So here's I had to show these wonderful pictures of, well, this one is of Staffa. If you've never visited Staffa off the northwest coast of Scotland, go and see it. It's one of the great sights of the world. So this is a phenomenon called columnar jointing in basalt. So when lava comes out of a volcano, it solidifies, it fills up some kind of lake, and so it starts cooling from the bottom and from the top. And you get a layer, for example, on the top of solidified lava, and the top of the layer is cooler than the bottom. And so the bottom tries to put the top into tension. And so somehow it wants to locally curl up into a little bowl. Well, this is one way of thinking about it. It wants to curl up into a little bowl everywhere, but it can't do that. And so it generates cracks. And the sort of the thing that most nearly approximates little bowls everywhere with cracks is, in fact, what you see in these situations. These hexagonal columns that are formed in which you see. This is in the Giant's Causeway in Northern Ireland. So these columns here are essentially have hexagonal cross sections. This is a wonderful example of cracking. Or you might have dislocations in materials. This is another kind of defect. So that's a place where something goes wrong with the regularity of the crystal lattice. So on the left, it's where you've where a plane of atoms are suddenly stopped, and on the right, it's where they've got somehow jogged down by one atomic layer. And then you get lines, so dislocation lines. So, for example, in this on the right-hand picture, it is the red line shown, and on this picture it would be perpendicular to the screen, more or less, where the middle is there. And then when you actually see them in experiments, they look something like, the lines look like something like that in the bottom picture. So this is another kind of defect that occur in materials. Or you can have phase boundaries. So materials, solid crystals undergo phase transformations in which they, at certain temperatures, the crystal lattice wants to change shape, e.g. from cubic to tetragonal. And so, and it may want to, so cubic to tetragonal means you have a kind of cubic lattice at a high temperature, and it wants to extend, say, in this direction, or you could equally extend in this direction or extend in this direction. So it has three possibilities. And the question is, it'll choose to do one possibility somewhere in the material and another one in some other part of the material, and it's all got to fit together geometrically. And so it forms these layers where it's alternately stretched in one direction and in a perpendicular direction. So this is a high-resolution electron micrograph, so each dot represents an atom. So you see that it forms these layers which are very, very thin. They're alternately about 6 and 10 atomic spacings. This is in nickel manganese. And this, if you go to the BBC website of about last week, this is something with my which my collaborator did, but is based on work we did. They discovered, essentially by mathematics, new materials that have fantastically low hysteresis. And there's an amazing video of this that you can see on the BBC website or on the Oxford Maths Institute website. And so the idea is that you construct this material so that it can form many more microstructures than normal by sort of tuning the composition of the material. And so usually when you cool crystals down through a phase transformation temperature, you get a very large hysteresis stretching maybe over 30 or 40 degrees or maybe more. And here the hysteresis is about 1 degree. And another amazing thing is that when you cycle this through the phase transformation temperature, you get a completely different microstructure each cycle, completely different. So it's a really, really remarkable material. But each of these interfaces you see on that zinc, gold, copper alloy is a jump in the gradient of the deformation, just as in this high-resolution picture. So basically, the message is this, that in all these theories of solids and fluids and liquid crystals and whatever, you often have a choice between different ways of modeling them mathematically. You either model them by equations which give in which the defect is represented by a singularity of the equations. Okay? So that's great in some sense, because you know exactly what you mean by a defect. You know exactly where it is. It's mathematically it's modeled by a singularity, or so that's like the ozone-Frank theory, or you model it by some other theory which gives more structure to the defect. So instead of, for example, representing a shock wave by a brutal discontinuity in the velocity between on some plane, it's smoothed out some way. And ideally, that will give you more information about the defect. But on the other hand, it's less easy to know where the defect is, or what it's a region somehow where things are varying rapidly, but exactly where, and it's not so easy to understand it. And a lot of current research centers on how you try to reconcile these two different kinds of models of defects. And so there's a lot of interesting stuff that goes on there. And this is just one example. So this is the kind of thing which I'm sort of interested in. I've not really gone into the sort of the details of the partial differential equations and how you try and understand these from the point of view of partial differential equations, because that's a bit technical. But I hope you got at least some kind of picture of sort of interesting phenomena that you see in these materials. Okay.
Are there any questions?
So I noticed that in the glaze picture and the mud pictures, the cracks meet at right angles.
Very good, yes.
The hexagons in the basket. What's going on there?
Okay, very good remark. So in glaze, the prevailing opinion is that when you what you see here is that when you have a crack and it approaches a free surface, it swerves in so that it goes perpendicular to the free surface. And so that's in some sense what you're seeing. You're absolutely right. Most of these things are so the question is, why? Well, you have to try and show that this happens using mathematical models. And actually, sort of the more recent kinds of mathematical models. Old theories of fracture, mathematical theories of fracture, essentially took a crack which was there, and then you applied forces, and it tried to tell you what happened to this crack. Okay, but it was not capable really of understanding nucleation of cracks, where there weren't, where a crack appears where one wasn't before. Or complicated things like bifurcations of cracks, so when a crack starts propagating and then branches off. So there are kind of newer theories which in some sense are primitive, because they can't at the moment really work for fast propagating cracks. But for slowly propagating cracks, they have as a true unknown the crack set. And that crack set could have, in principle, arbitrary kind of complexity. So you could certainly model this kind of situation using such theories. Now the hexagonal cracks, this is if you can see in the Fingal's cave, the Stafford thing here on the left, this is a situation where you can see the flow in cross-section. So there's also locations in Hawaii where you can do that. It's what's called the boiling pots. I know something about this problem because I worked on it myself, and I also had a student who I think has more or less the only real sort of mechanical model of this. And when you measure, what seems to happen actually in this situation is that when it starts cracking from the top and the bottom, it's not exactly, well, it's never exactly hexagonal, of course, but it's not nearly as regular as this. But because you can measure what's happening to the angles in these exposures, where you see right across the thing, you can see that there's a gradual evolution of the crack pattern as you go into the interior, where it becomes more and more hexagonal. And it actually happens in increments, you can imagine. The lava cools over a very long period of time. And as it cools, so it's begun to crack. It's cracked down to a certain level, and then the stresses build up as it cools more, and then it cracks a little bit more and goes a bit further down. So it's a very complicated picture there to try and see how to show that the optimal situation is hexagonal cracks. But I think that this argument that I gave about it wanting to sort of curl up locally into a bowl captures some of what is happening. That the easiest way to do that, I mean, if you want to arrange circles on a plane of a certain radius, and deal with cracks, then the hexagonal situation seems to be the easiest way to do it. That's probably as much as I could explain. It's a very good question, a very good observation.
And this sort of bit, I don't really understand the maths, but you get different kinds of simulation where the particle simulation, for instance, you get simulations of galaxies colliding.
Yes. Mm-hmm.
Sort of arms emerging.
Yes.
From just by running bulk crashes with heavy duty mass.
Yes.
Is there a different approach to saying here are the spiral arms and this is what's going to happen to them if you've got a model?
Well, I suppose yes. I mean, actually, these liquid crystal models are used in cosmology, but I forget now the exact context in which they're used. But I mean, I suppose that the simulations. Sorry.
Cosmic strings.
Cosmic. It's not. Well, yes, cosmic strings, but the simulations you're talking about, I mean, it could be done more or less by are done by molecular dynamics using more or less classical fluid models, right? So I don't think there's any, there's no sort of, that's what produces and of course gravity produces the spiral arms, as I understand it. Of course, I'm not an astronomer, but it is certainly there are striking similarities in what some of the singularities look like. I agree. Yes. Yeah, but I suppose that maybe there are black holes in places like this.
Okay, thank you so much for coming. Before you go, there are two announcements. I believe there should be some refreshments upstairs. And also, please join us next week. We will be hosting Dr. Alex Richardson, and the title of the talk is "They Are What We Feed Them." So I believe it's going to be on nutrition. And thanks so much for coming again.